And we're back and still better than ever in 18-2. We are looking at calculating KEQs, our equilibrium constants, and equilibrium concentrations. In this case, we're going to, and example number 4 says to calculate KEQ for the following reaction in the following scenarios. And so we have one reaction, and we are given 3 different scenarios, A, B, and C. So let's first go ahead and write out the equilibrium expression for this reaction. In fact, we already did this in a previous example where KEQ is going to equal the ammonia squared divided by the nitrogen raised to the first power and the hydrogen cubed, because of course there's a 3 out front there. And so now what we want to do is we want to take a look at the KEQ for all 3 scenarios. Now in scenario letter A, let's go ahead and do this in, say, red. Scenario A here. Notice that we have an initial concentrations of 1 molar for both reactants, and we have absolutely no product. And then here are the equilibrium concentrations after that dynamic equilibrium has been established. Of course, the reactant concentrations decrease because the forward reaction is going. The product concentration is going to increase because you started with nothing, and when you establish equilibrium, you are going to have something on the product side. And so now all we need to do is plug in those values into the equilibrium expression. So our ammonia goes on top, that's 0.157 molar, and that's going to be squared, divided by our nitrogen concentration, which at equilibrium is 0.921. That's going to be raised to the first power. And we have the hydrogen concentration is 0.763 molar, and that's going to be cubed. Now, the first question might be, why are we using the equilibrium concentrations and not the initial? Well, because the equilibrium expression is an expression of where the equilibrium position is, so you don't want to use the initial. The initial concentrations are going to change, and they're going to continue to change until the system reaches equilibrium. And so now if we simply solve, we get 6025. Now we don't typically write the equilibrium constant K with units. Again, this is KEQ. We simply just write out what the value is. Alright, so if we start with all reactants and no product, this is what the equilibrium constant is. Let's take a look at scenario letter B, scrolling down. In this case, notice that we have absolutely no reactant, no nitrogen, no hydrogen. We start with 1 molar ammonia. So we have all product and no reactant. In that case, the reaction is going to have to shift back to the reactant side. The product is going to collide with itself and reform some reactants. And these are the concentrations that it stops at. Notice that they are different concentrations than if you start with 1 molar reactants. So let's go ahead and solve for KEQ in this case. KEQ is going to equal, well, the ammonia is 0.203 molar. That will be squared. The nitrogen concentration is 0.399 molar. That's raised to the first power. And the hydrogen is 1.197 molar, and that's going to be cubed. Now if you solve that, what you have is 0.06, or evaluate it I should say, 0.06022 for our equilibrium constant. Notice that it's almost identical to the equilibrium constant in the previous example. Let's go ahead and take a look at scenario letter C. Go ahead and change up. Let's do this one in an orange color. Now in this case we have a mixture of everything. We have some reactant, we have some product. They are not the same values, and they're going to establish an equilibrium unless they're at equilibrium already. In this case, notice that the concentration of both reactant increases while the product concentration actually decreases. So this reaction shifts towards the left from these concentrations. And so now if you plug these in for KEQ, the ammonia concentration is 1.82 molar squared. The nitrogen is 2.59 molar raised to the first. And then the hydrogen is 2.77 molar, and of course we're going to cube that. And when you evaluate that, you get 0.06017. So looking at the various Ks, notice that they are pretty darn close to one another, and in fact, it does not matter what your starting condition is. The equilibrium will shift so that all the ratios are the same, meaning it doesn't matter if you start with only reactants, only products, or a mixture of both. The equilibrium will shift until the ratios satisfy the equilibrium constant. That's how equilibrium works. And in fact, what you would do is you would just take an average of those three. The average KEQ for those few trials there, those three trials, is 0.0602. And that would be, say, our accepted value for the equilibrium constant for that reaction at that temperature. All right? Now, in the next podcast, we're going to take a look at, scrolling down here, we're going to give you what KEQ is, and we're going to ask you to solve for an unknown concentration. We'll see you next time.